Hi, this is the final video of this course. And in this video, I would like to talk about Chandrasekhar limit of stars. This limit is important for compact stars. And this Chandrasekhar limit is named after famous Indian physicist Subramanian Chandrasekhar. He got Nobel Prize due to this kind of studies. And Chandrasekhar limit is important for compact stars. So the main topic of this movie is neutron stars and white dwarfs. But before going to stellar structures, I would like to introduce quantum physics very briefly. In classical mechanics, as you know, you can observe both position and momentum of particles at the same time. So when you observe the motion of basketballs, you can draw single orbit in XP plane. This plane is called phase space. But in small world, situation is different. When you consider electrons or positons or protons or atoms, in this case, quantum mechanics is important. And in quantum mechanics, you cannot measure both position and momentum at the same time. There is an equality between dx and dp. So when you want to measure positions accurately, due to this relations, the uncertainty in momentum becomes larger. This is one of big difference between classical mechanics and quantum mechanics. And the other important topic in quantum mechanics is Pauli exclusion principle. This says only one electron can fill one state. I think some of you know this principle used in chemistry. Let's consider atomic structures. In atoms, there is many orbits for electrons. K shell, L shell, M shell, and blah, blah, blah. But there is an upper limit to the number of electrons that can occupy in this one shell. For example, only 2 electrons can occupy K shell, and 8 electrons can occupy L shell. This upper limit for occupation number is due to this Pauli exclusion principle. And situation is the same for electron gas at low temperature. At low temperature, quantum effect becomes important. And in electron gas, there is an orbit, or not orbit, there is state that should be occupied by electrons. This is a kind of room for each electron. And only one electron can occupy one state in this X and P planes. So when you consider this position and this momentum, you cannot put 2 electrons at this position. This is Pauli exclusion rule for electron gas. And let's consider the consequence of this exclusion principle. Let's consider electron gas confined in this box. And in this case, the electron occupies these positions and momentums. And let's compress this electron gas. When it compressed, possible position decreases. It means the maximum value of X decreases due to compression. So you should put these large X electrons at different place. This is just here. You can put these electrons at higher momentum positions in XP plane. As a result, it should affect the pressure. This pressure is called degeneracy pressure and important at low temperature and high density case. Usually, stars are supported by gas pressures, but when you compress this gas sphere more and more and more, at some parameter space, this degeneracy pressure becomes important. In order to consider these evolutions, let's consider contraction of fixed mass gas sphere. I mean fixed M. In last two videos, I introduced three equations: mass conservation and force balance and equation of state. And here I will use two equations, this equation and this equation. And using these two equations, we can derive relation between pressure and density. This equation is a bit complicated. We don't use the relation between pressure and density. We just use force balance and mass conservation. And this equation means, okay, let's consider fixed gas sphere. And this gas, the mass of this gas sphere is m, and density is rho. And to keep this gas sphere, this kind of pressure is required. So we don't know equation of state, but if the pressure of this gas sphere is lower than this value, it should contract. And if pressure of this gas sphere is larger than this value, it expands. In order to make force balance, this pressure is required. And in log B, log rho plane, this relation is in single lines. And as the gas sphere contracts, the required pressure increases based on this relation. Okay, let's consider equation of state. This figure is very busy, but the axes are the same as before. This is log rho and this is log p. And at each region, the equation of state is plotted. At this parameter space, radiation pressure is important. And at this space, gas pressure is important. And at more high density region, this green line, on this green line, degeneracy pressure of electron is important. And this shaded region is prohibited by Pauli exclusion principle. You cannot contract this gas sphere beyond these lines. You cannot enter these regions. Okay, let's consider contraction of gas sphere with fixed mass. As it contracts, required pressure increases. And in this parameter space, gas pressure support this gas sphere, but required pressure increases, so the both pressure and temperature increases along these lines. And at this point, the evolution line encounter this degeneracy lines. And at this point, you cannot enter this region and cannot go beyond this point. Just stop at here. And at this point, gas sphere is supported by electron degeneracy pressure. And this star is called white dwarfs. Okay, let's consider one massive case. Start at here. In this case, the star, along contraction line, it evolves following this relation. But in this case, there is, this red line not encounter these green lines and just continue contractions. And at some density, its electron capture starts. So proton and electron makes neutrons. This is a formation of neutron star. In case of contraction of gas sphere with fixed mass, nature is different. But this is a kind of very brief one of ideal case, not in nature. Then I'd like to briefly talk about the neutron formations. As I mentioned, when electron gas is compressed, the electron at this point should move different positions for a high energy state. It means high pressure state, high momentum state from here to here. But in order to put this electron from here to here, we need to give some energy to this electron. This is noted EF here. And in more dense electron gas, this required EF becomes larger. And it just increases. Okay, then let's consider what happens if this EF is larger than mass difference between neutron and protons. As you know, protons are more stable compared with neutrons due to this mass deficit. But if EF becomes larger than this mass difference, making neutrons is more stable compared with putting electron from here to here. We need energy, EF, to put electron from here to here. And we need energy of this value to make neutrons. And if this energy is smaller than this energy, then making neutron is more easy for these electrons. As a result, neutron is created and neutron star is formed in this path. Then, question is the boundary between these two cases. For low total mass case, it increases along this line and encounter this green line. This case is white dwarf. And in more massive case, it cannot encounter green line and make neutron stars. And there should be boundary between these two conditions, something like this red line. Let's consider this boundary. Same as before, we can use these two equations. And using these two equations, we can derive relation between mass, pressure, density. So, okay. And as you can see in this figure, at low density, when the density is lower than low critical, the pressure is proportional to rho to the power of 5 over 3. But above this density, pressure is proportional to rho to the power of 4 over 3. I would like to use this condition as equation of state. When rho is smaller than rho CR, you can substitute this relation to these equations. And you can get relation between mass and density. Mass is proportional to rho to the power of 1 over 2. So for higher density, higher mass is realized. But above this low critical, pressure is proportional to this value. And when you substitute this relation to here, mass is constant. So it is not depend on density of gas spheres. So even if density is high, the total mass is constant. This is the relation between mass and rho and okay. And here it's rho CR. For low density, for density lower than rho CR, the mass is proportional to rho to the power of 1 over 2. But above this rho CR, for example, when we consider density at this value, then mass is constant. This value is constant. And for more dense case, mass is same. And this mass is called Chandrasekhar mass limit. And we can calculate this mass shown here, 1.4 solar mass. So when we consider a homologous gas sphere supported by the electron degeneracy pressure, there is a maximum mass of that star. This is Chandrasekhar mass limit. And above this value, there is no solution for these two equations. Okay. Let's start from mass. For mass lower than MCH, there is a solution for of densities here. But when mass is larger than MCH, there is no solution for density. It means there is no solution for these three relations. And this mass range is prohibited by these equations. This is Chandrasekhar mass limit. Okay, and if you want, you can derive this relation using the method in previous videos, but I would like to skip here. Here is a brief summary of contraction of fixed mass gas sphere. Sorry, not gas sphere, but kind of stars. When star run out of nuclear fuel, it cannot make energy and just contract. When this mass is smaller than Chandrasekhar mass limit, this gas sphere can be supported by electron degeneracy pressure. This case, the final star is called white dwarf. But if mass is larger than this MCH, this pressure cannot support the gas sphere. It continues contracting and make neutrons. This is the neutron star. And this neutron star is supported by nuclear force, not by degeneracy pressures. Sorry. And using nuclear physics, we can derive some kind of maximum mass for neutron stars. And above this mass, even nuclear force cannot support the stars. So it results in black holes. Okay. Okay, here is summary of this video. Thank you very much.